Welcome to Chapter 2 of the Autonomous Driving series. In this lecture, we move beyond perception to explore how self-driving cars actually make decisions and execute them. We'll cover path planning algorithms, behavior prediction, decision-making frameworks, and vehicle control. Then we'll survey the major industry players shaping the future of autonomous driving. By the end, you'll understand the complete pipeline from sensing the world to safely navigating through it. Path planning is about finding a safe, efficient route from point A to point B. The A-star algorithm works on grid maps, expanding nodes by combining actual cost with a heuristic estimate of remaining distance. It guarantees finding the optimal path, but can be slow in large spaces. RRT, or Rapidly Exploring Random Tree, handles high-dimensional spaces by randomly sampling points and growing a tree toward them. It's great for complex environments, but produces non-optimal, jagged paths. Potential field methods treat the goal as an attractive force and obstacles as repulsive forces, creating a smooth gradient to follow. However, they can get stuck in local minima. Lattice planning uses a pre-computed set of trajectory primitives that respect vehicle dynamics, making it popular in structured road driving. Modern approaches increasingly use machine learning. Imitation learning copies expert driving behavior, while reinforcement learning optimizes driving policies through trial and error in simulation. Predicting what other road users will do is one of the hardest problems in autonomous driving. Physics-based models use kinematic equations, assuming constant velocity or acceleration. They work for short horizons, but fail to capture human intent. Social force models add interaction effects, modeling how pedestrians influence each other's movement. Graph neural networks revolutionized this field by representing traffic scenes as graphs, where vehicles and pedestrians are nodes and their interactions are edges. This naturally captures who influences whom. Traitron++ combines recurrent encoders with a graph representation of the scene and a conditional variational autoencoder to produce multiple plausible futures. Transformer-based models, such as AgentFormer, go further, using attention to model temporal dependencies and multi-agent interactions simultaneously. They can generate multiple possible future trajectories with associated probabilities, which is critical because human behavior is inherently uncertain. A pedestrian at a crosswalk might cross or wait, and a good prediction model must capture both possibilities. Decision-making determines what action the vehicle should take given its understanding of the environment. Finite state machines are the simplest approach. Define states like lane keeping, lane changing, and stopping, with explicit rules for transitioning between them. They're interpretable and predictable but struggle with complex scenarios. POMDPs, or partially observable Markov decision processes, model uncertainty explicitly by maintaining a belief state over what's happening. They're mathematically elegant but computationally expensive. Knowledge-driven approaches encode driving rules and traffic laws as a structured knowledge base. Data-driven methods learn decision policies directly from large datasets of human driving. The most promising direction is hybrid approaches that combine learned policies with safety constraints and rule-based guardrails. This gives you the adaptability of machine learning with the safety guarantees of explicit rules. The autonomous driving industry is split between two fundamental architectures. The modular approach breaks the problem into separate components. Perception detects objects, prediction forecasts their motion, planning generates a trajectory, and control executes it. Each module can be developed, tested, and debugged independently. Waymo pioneered this approach, achieving remarkable safety records. The end-to-end approach, championed by Tesla, feeds raw sensor data directly into a large neural network that outputs driving commands. Tesla's FSD versions 13 and 14 use this architecture with vision-only input from 8 cameras. The advantage is that the entire system is optimized jointly, potentially avoiding information loss between modules. A hybrid approach sits between the two. Neural networks handle perception and planning, but explicit rule-based safety checks sit on top of the learned policy. Several supplier platforms are converging on this pattern. Each approach has trade-offs. Modular systems are more interpretable and debuggable, while end-to-end systems can potentially achieve better overall performance through joint optimization. Once a trajectory is planned, the control system must execute it precisely. PID control is the workhorse of engineering. It uses three terms: proportional, which corrects based on current error; integral, which corrects based on accumulated past error; and derivative, which corrects based on the rate of change. PID is simple, fast, and requires no model of the vehicle. However, it reacts to errors rather than anticipating them. Model predictive control, or MPC, takes a fundamentally different approach. It uses a mathematical model of the vehicle to predict future states over a time horizon, then optimizes control inputs to minimize a cost function while respecting constraints like maximum steering angle and acceleration limits. MPC recalculates at every time step, creating a receding horizon that continuously adapts. It's more computationally expensive, but handles constraints naturally and anticipates future conditions. MPC is widely used for trajectory tracking in autonomous vehicles because it handles vehicle dynamics and physical limits explicitly, though simpler controllers are still common in production driver assistance systems. Waymo and Tesla represent two fundamentally different philosophies in autonomous driving. Waymo, born from Google's self-driving car project, takes a safety-first approach. Their vehicles use lidar, cameras, and radar for redundant sensing. They operate as Level 4 robotaxis in geofenced areas, serving paid driverless rides in several U.S. metro areas. Their modular architecture with machine learning components has been refined over more than a decade of development. Tesla takes a scale-first approach with vision-only sensing using 8 cameras and no lidar. Their driver-supervised FSD system runs on a large consumer fleet, collecting real-world driving data at a scale no competitor matches. Recent versions moved to an end-to-end neural network architecture. Tesla argues that cameras alone are sufficient because humans drive with just vision. The key philosophical difference is clear. Waymo optimizes for safety within limited areas, while Tesla optimizes for broad coverage with incremental improvement from fleet data. China has emerged as a major force in autonomous driving, driven by supportive government policies and massive urban populations. Baidu's Apollo Go is one of the largest robotaxi services in the world, operating across many Chinese cities and serving a very large weekly ride volume. Their open platform approach has attracted hundreds of industry partners. Pony AI completed a U.S. listing and operates both robotaxi and robotruck services, with a strategic partnership with Toyota. WeRide has expanded beyond China into the Middle East and operates multiple vehicle types including robotaxis, robobuses, and robosweepers. Momenta takes a unique data-driven approach, starting from Level 2 driver assistance to collect data that feeds their Level 4 development, with BYD as a key partner. AutoX focuses on fully driverless operations in dense urban environments like Shenzhen. The Chinese ecosystem benefits from regulatory willingness to permit large-scale testing and deployment that moves faster than many Western markets. NVIDIA and Mobileye are the two dominant platform providers enabling autonomous driving for automakers who don't build their own systems. NVIDIA's Drive Thor processor provides an order of magnitude more onboard AI compute than earlier automotive platforms, enough to run complex models directly in the vehicle. Their software stack includes Drive OS for the operating system, DriveWorks for sensor processing, and Drive AV for autonomous driving. Their Alpamayo model is a state-of-the-art end-to-end driving model that goes from sensor input to trajectory output. Mobileye, majority owned by Intel, takes a different approach with their true redundancy architecture. They build two largely independent perception subsystems, a camera-only system and a radar and lidar system. Because each can perceive the scene on its own, a failure or blind spot in one does not propagate to the whole vehicle. Their IQ family of chips supplies the onboard compute. Mobileye offers two product tiers: supervision for advanced driver assistance and chauffeur for full autonomy. Most traditional automakers partner with one of these two platforms rather than developing everything in-house. Let's recap what we covered in Chapter 2. Path planning provides multiple algorithmic options from classical A-star and RRT to modern machine learning approaches. Behavior prediction has evolved from simple physics models to sophisticated GNN and transformer architectures that capture multi-agent interactions. Decision-making frameworks range from interpretable rule-based systems to adaptive learning-based methods, with hybrid approaches offering the best of both worlds. For control, PID provides simplicity, while MPC delivers optimal performance with constraint handling. On the industry side, Waymo leads in robotaxi safety and operations. Tesla is scaling vision-only autonomy across a large consumer fleet. And China's ecosystem is growing rapidly, with Beidou Apollo Go among the largest robotaxi services worldwide. In Chapter 3, we'll dive into the AI and deep learning frontiers powering the next generation of autonomous driving, including vision transformers, foundation models, and world models. See you in the next chapter.